Okay, my name is Kristian, and I'm going to speak about the Finnish pilot site. The Finnish pilot site consists of 23 district-heated single-family detached houses in Omenatarha, a part of Porvoo in southern Finland. The houses are recently built. Their average size is 160 square meters. Their annual heat demand is about 40 megawatt hours each, and the electricity demand is 6.1 megawatt hours in average. The average household size is 2.7 residents and typically consists of families with young kids. There are currently no renewable production in Omenatarha area. The local bio-CHP plant is within the range of the neighborhood definition, therefore 98% is already produced by local renewables. We're already very close to energy positivity level A. We will take a look at which steps are required in order to incrementally reach energy positivity. The pilot site is monitored by Energy Management System, the EMS, which is based on IBM Intelligent Operations Center in France. The EMS receives data from both the district heating billing meters and electricity billing meters via the local energy company, Energy. But it also receives electricity data which is measured by additional third-wave energy measuring equipment installed in each pilot household. This measuring equipment provides the project with less delayed, more fine-grained demand data even at appliance level. The main heat supply for the district heat network is a wood chip bio-CHP plant in Tolkien, 10 kilometers south of Porvoo. For covering the big demands during cold peaks, it's assisted with gas as a backup heat supply. The EMS is also connected to the North Pool spot market, from where it receives hour prices used for optimization and simulated trading. The EMS optimizations and simulations are also connected to the weather forecast service for the area. The EMS extends the pilot with a simulated wind turbine, a simulated heat storage, and a simulated electricity storage. The pilot site is, of course, also connected to the power grid. The EMS can be adjusted to optimize either for minimal cost, minimal CO2 emissions, or a mix of these. The size of the simulated energy sources are dimensioned to match our pilot. Our pilot consists of 23 households, but in real life, the CHP plant is serving a demand that equals 1,350 of such households, which is 59 times bigger. Therefore, we have scaled down the production numbers to match our pilot. For instance, the wind turbine simulation is 3.3 megawatts of power, but our pilot receives the amount of the simulated output divided by 59, which gives 56 kilowatts as a maximum power for the wind turbine. So here you can see the heat storage and the maximum CHP heat, how the supply matches the heat demand of the pilot site. These numbers are now all scaled down. The backup gas heat supply is considered to be unlimited since it is dimensioned to be sufficient. The heat demand is described using two circles, representing the maximum and the minimum observed values of the measuring period. You can see the simulated heat storage as a small circle to the right. The simulated wind turbine is able to match the electricity demand quite well during windy days. However, the maximum power of the CHP plant is only economically usable when there is a corresponding heat demand. The electricity storage has the same size as the heat storage. Let's take a look at how the EMS interacts with the pilot. Each pilot household has a tablet with the Home Energy Awareness app installed. The Home Energy app is displaying a neighborhood 24-hour energy demand and a 24-hour local renewable supply. It's also displaying the household electricity cost for today. And furthermore, it has a feature for displaying appliance level historic demand by clicking on an appliance icon. On one of the icons refers to the whole household. By clicking it, it will display a consumption chart of the previous 24-hour demand for that that home. The Home Energy app has also an augmented reality feature. It can be used for scanning the environment using the tablet camera in order to look for appliances. Once it recognizes an appliance, it will display the current consumption of it, and also a small gauge meter, which is calibrated according to the historical demand of that appliance. We have used tags to make the image recognition easier. The setup process would otherwise require slightly challenging image model creation for each appliance. Integrated appliances such as dishwashers and refrigerators are impossible to distinguish optically. Besides improving energy awareness of the residents, another very important feature is the notification. At the bottom of the screen, there is a banner where new notifications can appear. By clicking on a notification, it will open up a window containing an energy-related advice. These advices are part of the EMS demand-side management, since they request the residents to either avoid or prioritize some particular hours for appliance use. Notification can also relate to heat. In that case, it asks the resident to temporarily turn down or up the indoor temperature. For instance, this message tells the user to try to prioritize some hours for electricity usage. It would be particularly suitable hour for running washing machines, dishwashers, or perhaps heat the sauna. We have developed a service provider interface and the public screen interfaces for both the Finnish and the French sites. Pascal will soon talk more about them in detail. Furthermore, we have some interfaces for supporting the Finnish pilot. The Skafchar web portal, which, by the way, includes our Asemo real-time energy monitoring solution, and the Facebook page for the pilot area residents. I'm very happy to tell that we've got results that underpins our proposed business model for an EPN. 76% of the respondents of our survey, which was answered by 45 people, think that the joint procurement would make renewables such as PV panels somewhat more or much more interesting. Only 4% think that the approach is slightly less interesting. Our study showed that the people accept the home energy app approach, and the app received very good usability test scores. An interesting fact is that the pilot houses has an annual heat demand, which is almost 65% less than the national average heat demand per square meter for detached houses. The pilot residents themselves estimated it to be about 20% less than the national average. The low heat demand is mostly explained by the way buildings are constructed nowadays. The pilot houses consumes 26% less electricity compared to houses of our comparison group of similar age, size, and also district heated. Part of it could possibly be explained by the living lab work that the city of Porvoo and Posintro have conducted in the same area, using Asemo real-time energy monitoring interface for improving energy awareness. The energy awareness among the residents is quite poor, but an interesting result is that it's probably a good thing. They are consistently overestimating their own energy demand, own annual energy costs, and heavily overestimating the energy cost for using appliances such as washing machines. There might be a downside if the awareness would be improved. The EMS simulation and optimization results will still be calculated, but will be published in the impact report in the near future. The incremental path for reaching energy positivity will look like this. The Atlas urban planning tool is used for decision support at early phase. the user interfaces have a minor impact, but the energy management system optimizations and predictions are expected to have a significant impact. Together with the proposed joint procurement of renewables, which have turned out to be very welcomed, they will raise the area positivity level with more than one step. Omenata is already very close to being energy neutral. Approximately 60 square meters of additional PV panels would make it energy positive and thereby raise it with 2 levels. Thank you. Now over to Pascal's